Hey guys, so we've been talking about functions, and functions are become one of the main things we end up studying in this class and later classes. Just the way numbers were the things you studied previous to this, and one of the things you start learning how to do with numbers once you learn what they are is how do you combine them? You add them and subtract them and multiply and so on. So we're going to do the same thing with functions. We start with functions, and we can get more interesting functions by combining them. And we're going to look at a few ways to combine them. You'll recognize some of this will have addition and subtraction, multiplication, division. And then this last symbol is an open circle, and it's something called composition. That one's different than things that we do with numbers, but we'll get to that. So let's just start talking about how we put these things together. So I've got a handful of functions here, f, g, and x, and h. And so I'm just going to go through these. I'm just going to start with the first four operations, the ones we're familiar with from arithmetic. And there's no real big surprises when we combine these. So, for example, but I want to make this part clear, is that when we combine functions, we're creating a new function. And so, for instance, if I take the function f plus g, okay, so the way we should think about these symbols is just like when I write, just like when I write f of x, this is the name of the function, this is the input, the x is the input, and the whole symbol together becomes the output when we input x. This new function that we have here, this is the name of the function, right? This is our function. We call it f plus g. It's a new function. It's not f, it's not g, it's a new function. We have the same input, and this whole symbol, this whole collection of symbols is the output, right? Just like any other function we did. It just happens to have three symbols as its name, f plus g. And we put those extra parentheses there just to be clear what we're talking about, right? If we had other symbols around that way, it would separate it. So that's what our left hand is, just giving a name to the new function f plus g. The right hand side is going to tell us exactly what that function does. And so we'll write it's f of x plus g of x, right? In other words, what this function does is you take an input, you evaluate it at f, right? You evaluate it at f, you evaluate it at g, with g. So you get an input, you evaluate it, you put it into f, you put it into g, and you add those two things together, right? So it's a set of instructions, right? The instructions for f and g are implied, right? Remember, f and g are their own functions. F is the function that says take a square root, take an input, find its square root. G is the function that says take an input, double it, and add 1 to it. So if I were to compute, say, f plus g of 4, we get f of 4 plus g of 4. And we could do the work right there, or we might decide to come off to the side and say, okay, what's f of 4? That's the square root of 4, which is 2. What's g of 4? That's 2 times 4 plus 1, so that's 8 plus 1, or 9. And so this becomes 2 plus 9, or 11, right? So the output of this new function f plus g of f4 is 11, okay? No big deal there. Let's do one more. Let's do f plus g of -1. So we get f of -1 plus g of -1. This time I'll just write it out right here. We have the square root of -1 plus 2 times -1 plus 1. Well, 2 times -1 is -2 plus 1 is going to be, there's a -1 here. We get the square root of -1 minus 1. And so we hopefully notice that we've got an issue here. We cannot evaluate f at -1. And it doesn't matter that we were able to do something with g and get a number. We can't just throw away this part that doesn't, like, we often will say something like, oh, the function doesn't exist there. We got to be really careful what we mean by that. right? I might be tempted to say, well, this just doesn't exist here, and so my answer is -1, but that's incorrect. Our new function, f plus g, requires us to evaluate f at the input. So if I can't evaluate f at the input, the whole thing breaks down. And so there is no way, we cannot add does not exist and -1 together. And so the function's input doesn't exist there. And so it illustrates a point which the domains, we have to consider both functions when we're looking at the domains when we combine functions, okay? So in this case, right, when we're adding these two functions together, we should be thinking about the domain of each of these numbers, which we didn't really talk about before. Our domain of g is all real numbers. The domain of f is going to be all non-negative numbers. And so to evaluate these, we need both of these. We need our input to be in both domains. And so the intersection of all real numbers and all the non-negative numbers is just all the non-negative numbers. So we have to put in only non-negative numbers. All right, let's do another one. All right, let's do division. Let's look at f, a new function, f over g of x. All right, so again, we have a new function whose name is f over g, right? Or however you want to say that, f divided by g. I like f over g of x. That's you're right. Input, the whole thing is the output. The right-hand side, I'm going to write instructions for what that function does. What we mean by this, f over g, is to evaluate f and evaluate g, and then divide them, right? So f over g, let's just make it simple on ourselves, of 4, we've already computed these. Well, f of 4 we decided was 2, g of 4 was 9, and so we get 2/9. Okay. Let's think about domain on this one before we make an error. Going back to our original functions, we know that the domain of f is only non-negative numbers, and then g is all the real numbers. So certainly, when we think about our domain, we should be considering only numbers greater than or equal to 0, because we know if we do anything other than that, if we do any negative numbers, f is broken. So we can automatically throw all those out. G can take any number, so that's fine, but we have to remember we've decided to divide here, right? Let's add a little step here. We might see what this thing looks like in another way by writing this, right? I'm just writing the expressions for f over g, and we see that we've got a fraction. I mean, we already knew that, but maybe it's more explicit here. We need to make sure that that denominator is not 0, right? And so let's consider that denominator, 2x plus 1 is equal to 0. 2x is equal to -1, so x is equal to -1/2. So we have to make sure x is never equal to -1/2, right? If we put that in, then we would have a 0 in the denominator. However, we don't have to worry about that because of our first restriction. So luckily, this landed outside of what we already decided, and this domain will be perfectly fine because we'll always be able to evaluate f, and we'll never hit the problem of g being 0. Let's consider a similar function. If we looked at g over f of x, this is now 2x plus 1 over the square root of x. Thinking about the domain, we will have no issues in the numerator. G can take any number, and we can have any number in our numerator. We know that f can only take non-negative numbers. That would include 0, right, as we had above. However, since it's now in the denominator, we can't have a 0 down there. And so our domain becomes slightly smaller. We can only have the strictly positive numbers because that 0 would cause an issue when we tried to divide, right? So in general, right, as we combine functions, domains are going to become complicated at times, right? We see, and it's different for the different kinds of combinations. When we add or subtract, we need to look at the intersection of the two functions because we can only put in inputs where both of them are able to be evaluated. When we're dividing, we have the same condition. We have to have both functions able to be evaluated. And we have the condition that the one in the denominator can't evaluate to zero. So we can only look at parts of the domain where it's where the denominator function does not evaluate to zero. Okay, let's do a couple more. Let me just see if this works. I'm new to this function, so I'm still learning something. Okay, there, I've got my functions with me now. Let's look at, oh yeah, let's look at multiplication with something like h of x. Let me throw one more function in here. Let's just thought of a situation I want to show. So let's look at k of x equals, I don't know, let's do something like x squared minus 2x. Okay. And let's suppose we wanted to look at the function h times k of x. Right? What we mean by this is we evaluate h, we evaluate k, and we multiply those two things. Right? So for example, let's do h times k of 3. We would have h of 3. So that's going to be, well, let's just write it out. H of 3 times k of 3. H of 3 is 1 over 3. K of 3 is 3 squared minus 2 times 3. So that's 1/3. 9 minus 6. Oh, I just picked that randomly, but we end up with 1, right? 9 minus 6 is 3 times 1/3 is 1. So h times k of 3 is equal to 1. Okay. Now, let's do this slightly differently. We will often see people, sometimes those people are ourselves, taking our functions and writing them out more explicitly, right? We have h times k, but I could write this as 1 over x times x squared minus 2x. And I might even be tempted, x squared minus 2x can be written as x, factoring out an x, times x minus 2. And you notice we have 1 over x times x. We can cancel those x's, and we're left with x minus 2. All right, h times k over x. All right. And what I've just written is mostly correct. For example, if I take this and compute h times k of 3 like we did just a moment ago, and just plug it into this equation, I get exactly what I got previously, right? Which is expected, right? There was almost nothing wrong with our algebra. And so when we evaluate or when we manipulate things algebraically like this, what we're supposed to be getting is equivalent expressions, things that are exactly the same, just written differently. This one, though, however, has one small problem, and that came in the step between these two lines when we canceled that x. When we cancel factors in the numerator and the denominator, that are expressions, something including a variable, something that can take on a multitude of values, we have to consider what would happen if that value was 0, right? Because the reason we get to cancel them, right? The reason we can take something like x over x and write 1, well, if it's 2 over 2, we can certainly write 1. The reason this is slightly problematic is that certainly works if x equals something like 2. 2 over 2 is equal to 1, or if x equals something like 3 over 3, it's equal to 1, right? For all these inputs, this is true. However, if we put in 0 for x, this is not equal to 1. 0 over 0 is not defined. And so there's a problem that this expression of our function, h times k of x equals x minus 2, is defined for 0 in here, because we can certainly put in 0 minus 2 and get negative 2. But if we go back to our original configuration, h times k of 0 equals h of 0 times k of 0, h of 0, which is 1 over 0, is not defined. And so the function, this multiplication breaks down. We can't actually compute it. And this is the definition of the multiplication. And so this is the one that matters. The 1 over 0 is not defined. And just because we were able to divide it away or cancel it away doesn't fix that problem, right? This might feel a little bit too technical, all right? Because if we graph these functions, h times k is going to look exactly like the line x minus 2, right? This is just going to be a line. Let's throw in a set of axes. So x minus 2 is going to look something like this, right? This line. And the only difference between the expression I have over here and this expression is that there's a hole at 0 for the original expression, right? So they really are almost identical. There's just a hole there for the original expression. However, these functions might represent something. I mean, that's the more interesting thing to use functions for, right? Mathematicians love to play with this stuff, but scientists actually use these functions to represent things. And if that thing isn't defined at 0, it doesn't matter that you're combining it with something else. There might be a reason it doesn't exist there, that you can't do anything with it at that value. And so pretending like we suddenly fixed it is not good practice. And so there's a good reason why we have to consider that. And so it's fine to do this kind of simplification, right? It certainly makes computation easier. We just have to be this algebraic step, and this goes for anything we're doing. When we divide something we don't know about, we have to consider the case that it's 0. And that move is illegal when the thing we're canceling is 0. And so we just have to make a note. This is true. H times k of x is equal to x minus 2 in all cases where x is not 0. So for all other numbers, that's going to be the case. So we just have to make sure we're not forgetting that little fact. Okay, so let's move on now to that new symbol that we saw. There we go. Here's my functions. We'll probably do some other ones that we saw at the beginning, which is this open circle, and talk about what that function is. So let's just jump right in and do the following. F, that open circle, g of x. Okay, so again, there is our new function name. The way we say this is f composed with g. Okay, and the definition is a little clearer, is written this way. Okay, let's think about what this means, right? We've got a function here, f, and then it's parentheses, right? What goes into parentheses of a function but its input? The input is g of x, right? Which is another function. So remember what g of x, this whole symbol is an output, is some number, right? That number is becoming the input to f, right? But first you have to get this number. How do you get that number? You put an input into g, and g spits out a number. So we started reading left to right because that's how we're used to reading, but really the best way to understand this is from the inside out. We start with x. That's our input. X is given to g. G does whatever g does. When g does whatever g does, it spits out a new number. That new number is given to f, and then f does what it does and spits out a new number, right? We could make a little diagram, right? If this is the domain of g, and there's some value x, g takes that to g of x. Then g, I don't know if you can hear that. I've got a toddler yelling hello. Then g hands that over to f, and f takes that to a new point, f of g of x. All right, this is our diagram of how this function works, and together it's making this new function f composed with g. Okay, so that's the idea of this function, of this composition function. One other way to think about it before we get into the, we'll actually compute some. You know, if we think of G as a set of instructions, we get an input, we do some stuff, we get an output, and we think of F as a set of instructions, you get an input, you do some stuff, you get an output. Right? We have an f and g here, right? The function f takes the square root, the function g doubles and adds 1, but more abstractly, all functions can be thought of this way, some input, some instructions, and an output. What a composition does is makes a connection here. Starting with g, you input, follow the instructions, your output gets turned into the input of f, which then spits out its own output. Okay, so that's another way to think of this. We can say we concatenate the instructions, right? Putting them together. So that's another way we're going to think about composition. But let's actually look at what it looks like in practice. So going back to this function f composed with g of x, or we sometimes say f of g of x. Let's compute f composed with g of, let's just pick something easy. Let's pick 4. All right. So what this means is f of g of 4. So if we look at this, g of 4 is a number, right? Let's come over to this. I'll do it below. G, actually, I forgot. I've got, oh, I thought there was a way to scroll to the side, but I'm not going to worry about it. G of 4, we can evaluate. That's 2 times 4 plus 1 is equal to 9. So that g of 4 is equal to 9, so we can just replace the g of 4 with 9. And then f of 9 is just taking the square root of 9. So we get 3. So f composed with g of 4 is equal to 3. Right? In this little picture up here, we took the number 4. G took that number 4 to 9. F took that number 9 to 3, right? That's our, I know this diagram's getting a little obnoxious, but that's our little picture, right? If we think of the whole composition function, we don't have to worry about all the details. Our composition function takes the number 4 over to the number 3. Okay, let's do another example. Let's do f. See if I can get rid of this. F composed with g of -2. So we have f of g of -2. G of -2, just come off to the side here. G of -2 is 2 times -2 plus 1. So -4 plus 1 is -3. So we're replacing g of -2 with -3. F of -3 is the square root of -3, which is not defined. Okay, so this is another example where we didn't consider the domains enough here, right? Going back to this diagram, which I know is now fairly obnoxious, but if you, let's highlight some parts of it in red. This number x that we choose has to output a number g that's actually in the domain of f for f to be able to do something with it. So we have to start in the domain of g, but we can only be in the parts of the domain of g that give numbers that land in the domain of f. For example, the one we just did, we started at -2 here. G took it to a number that's outside the domain of f. And so f didn't know what to do with it. F couldn't do anything with it, right? Because we couldn't take the square root of that negative number. So it's a much more complicated thing to think about, that we have to take inputs for g that land in the domain of f. One way that might make this a little easier to think about in this case, we can write this f composed with g of x, or f of g of x, as f of 2x plus 1, right? That's what g is. Sorry, that equal sign got a little bit out of control. So we've got f of 2x plus 1, which means to make 2x plus 1 our input to the square root. Looking at that, it becomes fairly obvious we need the input to the square root in this case 2x plus 1, to be greater than or equal to 0. 2x is greater than or equal to -1. Sorry, there's I don't know if that noise is getting picked up, but there's some little ones running around. I think they've left for good. I think they got the message. So anyways, we've got this inequality. 2x plus 1 is greater than or equal to 0. 2x is greater than -1, or x is greater than -1/2. So when I put in the number -2, that's below our limit. And so this gives us the domain of this composition function. Okay. Let's do one more thing. Maybe more than one more thing. Let's just notice that if I do g composed with f, or g of f of x, right, I can write this out as g of the square root of x, or 2 square root of x plus 1. Let's compute this at 4, right? So remember up above, we did f of g of 4, and that came out to be 3. Now g of f of 4, we can compute, and I'll use this new expression for it. 2 times the square root, sorry, that should be a 4. 2 times the square root of 4 plus 1 is 2 times 2 plus 1, so 4 plus 1, or 5. So g composed with f of 4 is equal to 5. And two things to notice. One, we computed this slightly differently. Instead of computing f first and then g of the output, we kind of just wrote the whole expression together. And that's perfectly valid to do with the same conditions that we had up above. We have to make sure we're not, when we combine them, we might simplify things or combine things and make sure we're not doing something like canceling some zero factors. But maybe more importantly right now, or equally importantly at least, notice that these two functions are not the same. In other words, composition doesn't commute. You can't expect to change the order and have things work the same, right? If we're multiplying functions, f times g of x, that's exactly the same function as g times f of x, right? Because all this means is compute f, compute g, and multiply them. And this means compute g and compute f and multiply them. And we know multiplication commutes, right? Those two numbers are going to be the same. We're just switching the order and multiplying them, but that's perfectly reasonable thing to do. But with composition, we don't have commutativity. You might find some examples where it does work out, but in general, it's not going to work out. Okay. All right. One last thing. So let's start with a new function. Let's do f of x equals, let's do something like x squared minus 1. Okay. So I want to keep this notion of over here, I'm going to think of f as a set of instructions, right? We get an input, we square the input, and we subtract 1, and then we output, right? That's our function. That's what f does. Okay. So sometimes, and we'll have many reasons to do this that we'll see later, but for now, let's just think of it as it's a thing that ends up happening. We will do something that we don't typically call composition of functions, though it really is. Some people do. It's just not always thought of that way. And that will be, we'll do something like this. For various reasons, we might want to change our input, right? That something's going on, that the input, whatever we get, we want to do something, we're preparing it for our function. And so we might write something like this, say 3x plus 1, right? Let's think about what this does to a function, right? We input a number x, but we don't square it and subtract 1. The first thing we do is multiply it by 3 and then add 1 to it, right? So we've added these new instructions. We take our input, we multiply by 3, we add 1, and we output, right? And whatever that output is, then f does its thing. And so what we're actually doing is exactly the same thing that composition does, is we're adding together some sets of instructions, or concatenating some sets of instructions. We've got this one set. We just didn't name this a function, but I could have called this something like g, and then we'd be looking at f composed with g when we have all of the functions, right? Well, so in any event, we treat it very similarly. And often what we'll just do is we'll put that new input in place of x. We might decide it's nicer to 9x squared plus 6x plus 1 minus 1 and 9x squared plus 6x, because those ones cancel. So there's this new function that we've gotten by adding this set of instructions to the beginning. In other words, we're kind of doing a subtle composition of functions. But everything else after that works the same, right? We can f of let's put in x equals 2, so we'll have 3 times 2 in there. And we can think of this as 9 times 2 squared plus 6 times 2, 9 times 4 plus 12, or 48, okay? And so we've created a new function, which we might also want to give a name to. Just we'll also see ourselves doing that. That we don't, if we're creating this function for something, we don't also have to like keep that record with us all the time that it came by building this thing. It just might be something we use, but that's down the road. So in any event, I just wanted to put that in there, this extra kind of composition that we will do quite often. And in fact, in the next section, we'll dig into the details of this kind of composition, or a certain set of these kinds of compositions that we call transformations. But that's for next time. Okay, that will be it for now. Thanks, everybody. I will see you next time.